Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this video in which we'll go through everything you need to know about probability and functions for your final exam. So I'm going to cover the topics listed on your screen here. Let's get started with the sum of probabilities. So probability is the assigning to random events a number to indicate how likely they are to occur. The number we give them is always between 0 and 1. So the closer an event's probability is to 1, the more likely it is to occur. The closer an event's probability to 0, the more unlikely it is to occur. So if I say, what is the probability of an event, you must respond with a number between 0 and 1 that indicates how likely it is to occur. Now, just as percentages add to 100%, probabilities add to 1. So let's look at this question here. Bias four-sided die has 4 faces labelled 1 to 4. So this says the probability you roll a 1 and the probability you roll a 4 is 2 over 9. Now, what would be the probability I roll a 2 or a 3? So we know that all of these probabilities must add to 1. And the reason is 1 means certain. We are certain if we roll this die with faces labelled 1 to 4 that we will get a 1 or a 2 or a 3 or a 4. Now, we know that the probability of getting a 1 and the probability of getting a 4 are both 2 over 9. We also know that the probability of getting a 2 and the probability of getting a 3 are the same. So I could easily just replace probability of 3 with probability 2 here because they are the same. So let's go ahead and solve this equation. So obviously 2 over 9 plus 2 over 9, I can just write that as 4 over 9. And I can write the probability of getting a 2 because I'm adding it to itself. I can just write that as 2 times the probability of a 2. So to calculate what the probability of a 2 is, this is a really easy linear equation to solve. I simply just subtract 4 over 9 and then divide by 2. So I get 5 over 9 divided by 2, which is 5 over 18. The probability of getting a 2 is 5 over 18. And that makes sense because 2 over 9 plus 2 over 9 plus 5 over 18 plus 5 over 18 is equal to 1. So if I roll the die 450 times, how many times would I expect that I don't roll a 3? So probabilities adding to 1 can also be very useful when you're trying to find the probability something doesn't happen. So I just figured out in the previous example, the probability of a 2 is 5 over 18. So the probability I roll a 3 is 5 over 18 because I was told that they were equal. So the probability I don't roll a 3, I write it like this. This dash means not. Probability of not getting a 3 is just 1 minus the probability I do get a 3, which is 13 over 18. So if I roll a die 450 times, I would expect the number of times I don't get a 3 is 13 over 18 times 450. And that just equals 325. That's the number of times I expect I'd get either a 1, a 2, or a 4. So the reason this works is because this number 13 over 18 is what we call theoretical probability. So it's saying theoretically, if I were to roll this die here heaps of times, I expect that I will get a 3 5/18ths of the time. Every 18 times I roll it, I would expect that I would roll a 5. Of course, that may not happen in reality. But that's what theoretical probability is. It's the proportion of times something should happen. Just as the probability you toss a heads is a half, you expect that if you toss a coin heaps of times, heads will come up half the time. So that is how we do expectation. So let's now move on to the probability formula. Okay, so how do I calculate the probability of an event from scratch? I gave you enough information in the last question, but what if we don't know anything about the probability? How do we calculate it? Well, this is the formula for probability. The probability of an event is the number of ways it can occur over the total number of outcomes. We just call this NS because it means number in the sample space. So let's look at this question here. Team of 5 people to be chosen from 8 boys and 6 girls. What is the probability the team consists of at least 1 boy and at least 1 girl? So we're going to first find the probability that there are no boys on this team. In other words, what is the probability if I pick 5 people from a group of 8 boys and 6 girls, what is the probability that all of the people chosen are girls? So the way I figure out that probability, I'm going to calculate the number of ways this can happen over the total number of outcomes. Now, for this particular question, because I'm taking a group of objects and choosing some of them, combinations are an effective tool. They're counting tools. They're going to help me count this and count this. So, the probability that I pick no boys and all girls, how many ways can I pick all 5 girls if there are 6 girls to start with? Well, that number is just 6C5. The number of ways I can pick all girls, I'm picking 5 girls from a group of 6. So, what is the total number of way to pick 5 people from a group of 14? So I have 14 people to choose from, and I'm picking 5. This is the number of ways it can happen. This is the total number of outcomes. So 14C5, if I use my calculator, is actually 2002. There are 2002 different ways you could pick 5 people from this group of 14. The number of ways that you could pick 5 girls from a group of 6, 6C5 is just 6. That makes sense. Each time you pick a different group, there's one possibility for the girl that's left out. There are 6 girls in total, so there are 6 ways I could do this. So similarly, the probability that I pick no girls, the probability that all of the people chosen are boys would be 8C5. So the number of ways I can pick 5 boys from a group of 8 is 8C5, all divided by 14C5. The number of ways I can pick 5 people from a group of 14. So using my calculator, 8C5 is just 56, and once again, 14C5 is 2002. So the probability that I pick either no boys or no girls, I can just add these up. So these two events are called mutually exclusive. They can't both happen. I can't pick a team that is no boys at the same time I pick a team that is all boys. That doesn't make any sense. So when you have 2 events that are mutually exclusive, that can't both happen at the same time, the probability that either of them happens is just the sum of their probabilities. So the probability that one of these things happen is just those 2 probabilities added together. So that's the probability that I get no boys or no girls. The probability I get at least 1 boy and at least 1 girl is actually just 1 minus this. So why is that? Well, these 2 events are complementary. If you get at least 1 boy and 1 girl, that means you don't have all boys or all girls. This event is the same as this event not happening. So as I said, sum of probabilities, if you know the probability that an event happens, the probability it doesn't happen, just 1 minus that event. So I get 970 over 1001. Sometimes, if you want to calculate the probability of an event like this, it's easier to calculate the probability it doesn't happen and subtract from 1. Because the other way to do this, we'd have to find the probability that you get 1 boy and 4 girls, 2 boys, 3 girls, 3 boys, 2 girls, and so on. It would take too long. This way is a lot easier. So we used combinations here as counting tools to help us with probability. It turns out combinations are very useful in binomial expansions that we'll now look at. So here we have Pascal's triangle, and this is related to combinations. So remember, Pascal's triangle starts with row 0, and in each row, the first one is called entry 0. So the number that is in row n, entry r, is actually equal to NCR. So for example, if I wanted to, from this, calculate 5C2, I go to row 0, 1, 2, 3, 4, 5, row 5, entry 0, 1, 2. 5C2 is equal to 10. So what does this have to do with binomial expansion? So binomial expansions are where you have two terms in a bracket raised to a power. So this is saying x minus 3 multiplied by itself 4 times. Now that would take forever. It takes so long to do without the shortcut. So this is how you expand brackets like this. So you start with the highest power of x, so this will be x to the power of 4. So with each subsequent term, I decrease the power of x by 1, and I increase the power of x by the second thing by 1. So the second thing is minus 3. So the next one is x cubed times minus 3 to the power of 1. So with the next term, I decrease the power of x by 1, and I increase the power of minus 3 by 1. And then I do it again until there's no more x's. So that will be the next term, and the final term will be minus 3 to the power of 4. So you're probably thinking, well, what does this have to do with combinations? Well, each of these terms, 1, 2, 3, 4, 5 terms, needs a coefficient. That coefficient comes from Pascal's triangle, and Pascal's triangle contains all these NCR values. So because this is power 4, I'm going to look at row 4 of Pascal's triangle. If I've written the terms in order like I said to here, then you can just write the coefficients so easily. The coefficients are 1, 4, 6, 4, 1. The exact same numbers in that row of Pascal's triangle. So I can just clean this up a bit. So the first term is just x to the power of 4. So the second term, 4 times minus 3, minus 12, x cubed. And then the next term is 6 times minus 3 squared. The next term is 4 times minus 3 cubed. And then the last one, minus 3 to the power of 4. This is what I would get if I times x minus 3 by itself 4 times. Doing it this way is just much, much quicker. All right, let's now move on to conditional probability. So the idea behind conditional probability is this. Sometimes, if an event happens, it changes the probability that another event will happen. So this line in the middle here means given. So we read this as the probability of A given B equals the probability of A and B, the probability they both happen, over the probability of B. So whichever one comes second here goes on the bottom. So this is saying what is the probability A happens if we know that B happens. Sometimes that will change the probability of A happening. If B's happened, sometimes it won't. So let's look at these two examples. So we'll start with this one. So I pick a card from a normal deck of 52. What's the probability the card I pick is a king, given that it is a heart? So I'm saying I've picked a card and I know it's a heart. What's the probability it's a king? So in other words, we're calculating here the probability the card is king given that it's heart. So I'll use K for king and H for heart. So our formula at the top, it's the probability that both happen, that I get a card that's a king and a heart, over the probability of heart. As I said, whichever one's listed second goes on the bottom. So the probability that it's a king and a heart is 1 over 52. In a deck of 52, there is one card that is both a king and a heart, i.e. the king of hearts. Now the probability of picking a heart is 1 over 4. There are 4 suits: hearts, spades, diamonds, clubs. Hearts is one of them. So if I put that on my calculator, I get 1 over 13. The probability I pick a king, given that I pick a heart, is 1 over 13. But wait a minute, that's just the normal probability that I pick a king. If I just picked a card from a deck normally, the probability is 1 over 13. Doesn't matter whether it's a heart or not. So what we can see here, me telling you that the card was a heart hasn't changed the probability that the card I pick is a king. So we call these events independent. The probability that it's a king wasn't changed knowing it's a heart. So whether the card is a king is independent of whether or not it's a heart. The fact that the card is a heart, the fact that I know that this event happened, did not affect the probability that this happened. That's what independence means. So let's look at this example here. Roll a normal 6-sided die. What's the probability? The number I roll is a multiple of 3, given that it's greater than 2. So we're looking for the probability. The number is a multiple of 3. I'm just going to write M3 for multiple of 3, given that it's greater than 2. So let's figure out the probability that both happen. Multiple of 3 and it's greater than 2 over the probability that the number I roll is greater than 2. Okay, so on a die there are 6 outcomes, 1 to 6. How many of them are a multiple of 3 and greater than 2? Well, there's 2 such outcomes. I could roll a 3 or a 6. Both of them are multiples of 3 and also greater than 2. So the probability both of these events happen is 2 over 6. So what's the probability the number I roll is just greater than 2? So I could get a 3, 4, 5, or 6. So there are 4 possible outcomes out of 6 in total. Now, if you put this on your calculator, you get 2 over 4 or a half. So the probability that the number I roll is a multiple of 3, given that I know it's greater than 2, that's equal to a half. But see, the thing is, if I just roll a die, the probability of a multiple of 3 is normally 1/3. There's 2 ways it can happen. You can get a 3 or a 6 out of 6 in total. So what happened is that the fact that I know the number is greater than 2 increases the chances it is a multiple of 3. That makes sense. These are the possible outcomes of a die. So normally I have these 2 possibilities for getting a multiple of 3. So it's 2 out of 6. But if I get rid of these 2 by telling me that the number is greater than 2, you can see now it's 2 over 4. Now there's a greater chance of rolling a multiple of 3. So here, this event happening, the number being greater than 2, actually did affect the probability that the number was a multiple of 3. So in this case, we say the events are not independent or they are dependent, because the outcome of one affected the chances of the other happening. So we're going to look more now at independent events. So more formally, 2 events A and B are independent if any of these is true. So if 2 events are independent, it means that one does not affect the probability of the other. Just like on the previous slides, the events getting a heart and getting a king were independent because the fact that I got a heart did not affect the chances it was a king. Another way to say that 2 events are independent is that probability A given B equals probability A, or probability B given A equals probability B. So what this is saying, if B happens, the probability that A also happens is just its normal probability. In other words, B happening did not affect the chances that A happened. Now, just so you know, if this is true, then this will be true. It is impossible that one of these is true and the other is false. So if this is true or this is true, the events will definitely be independent. So it turns out that if 2 events are independent, the probability of A and B, the probability they both happened, is just the product of their respective probabilities. This is a very useful formula for figuring out the probability that both events happened. So let's look at this question here. Bag contains 3 red, 2 blue, and 1 green marble. 2 marbles picked one after the other. What's the probability that I pick 1 red and 1 blue marble? So it turns out the answer will be different if the marbles picked are with replacement or without replacement. With replacement means I pick the marble, put it back, and then pick a second one. And here I pick a marble, don't put it back, and then pick a second one. So let's look at this one here. So I want the probability that I pick one red and one marble. So I could pick a red marble first and then a blue marble, or I could pick a blue marble, then a red marble. So these two events are mutually exclusive. So to find the probability this or this happens, I just add together their probabilities. So the probability I get a red marble on the first go is 3 out of 6. There are 3 red marbles and 6 marbles in total. So if it's with replacement, that means I've got a red and I put it back. The probability I get a blue on the second go is 2 over 6. So for getting a blue then a red, it's just the same but a different order. 2 over 6 times 3 over 6. So if I add these together, I get 1 over 6 plus 1 over 6, which equals 1/3. So that is my final probability. So how would it change if the marbles were picked without replacement? Well, it would still be the same possibilities. I could get a red and a blue, or a blue then a red. So the probability I get red then blue. So the probability of getting red on the first go is still 3 out of 6. But if I get red on the first go, the probability to get blue on the second go, there are 2 blues but only 5 marbles left, because I took one of the reds the first go and didn't put it back. Similarly, for the next one, probability I get a blue the first go is 2 over 6, but the probability I get a red the second go is now 3 over 5, because there are only 5 marbles left. So the only difference between these two was the probability on the second pick. So if I add these up, I get 6 over 30 plus 6 over 30. I actually get 2 over 5. So this is about 40% and this is about 33%. So it's a little more likely that I'll get a red and a blue if the marbles are picked without replacement. And the reason for that is it makes it less likely, if it's picked without replacement, it's less likely that I'll get both red or both blue. So that's how independent events can help with calculations. Finding the probability I get a red and a blue, or a blue and then a red, is so much easier knowing the events are independent. So independent events give us a nice way to calculate the probability that A and B happens. Now let's look quickly at the probability A or B happens. So the good thing about this rule is it works for any events A and B. It doesn't matter whether they're independent, mutually exclusive, or whatever. So for any two events, probability of A or B, that's what this symbol means here, it equals the sum of their probabilities minus probability of A and B. And of course, if A and B were mutually exclusive, this would just equal 0. So the reason for that, we're about to go on to Venn diagrams, but just to show you, if I have two events here, say A and B, the probability they happen is the probability we're in this circle plus the probability we're in this circle. You can see that I've shaded in the middle twice. This region here is both. It's the region A and B. That's why I subtract this probability here, because when I add A and B, I've included this middle region twice. I've double counted it. So let's try this question here. I pick a card from a normal deck of 52. What's the probability that is either red or an ace? So I'm going to use this formula here because we're talking about OR. Probability of red or ace. So to do this, I'm going to take the probability that it's red, the probability it's ace, and add them together. And then I'm going to subtract the probability that it is both. So the probability I pick a red card is just a half. Every card is red or black. The probability of getting an ace is 4 over 52 or 1 over 13. There are 4 aces in the deck of 52. The probability of both is the probability I pick a card that's both red and an ace. Now there are 2 red aces in the deck. Ace of hearts, ace of diamonds. So it's 2 out of 52. So if you add up all these together, you get 28 over 52 or 7 over 13. And how easy is that? All right, let's now look more at Venn diagrams. So Venn diagrams, as well as two-way tables, they help us display information about two or more sets. So let's look at this question here. Class of 30 students, 8 blondes, 16 blue eyes, 11 with neither. What's the probability that a student chosen at random has blue eyes given that they have blonde hair? And we'll also figure out the probability they have blonde hair given that they do not have blue eyes. So this is a question involving two sets, blonde hair and blue eyes. So all Venn diagrams and two-way tables do is give us a way to display this information conveniently. So we'll set up a Venn diagram, starts with a rectangle and two circles, one for each set. So I'm going to let A be the set of students with blue eyes and B the set of students with blonde hair. I'm just going to go and write in the number in each set. Now you might be thinking 8 plus 16 plus 11 is 35. How does that make sense? Well, that means we've overcounted by 5 because there were only 30 students. That means 5 are in both. There are 5 students I must have double counted. I counted them in the blue eyes category and the blonde hair category. So 5 go in both. When you're dealing with Venn diagrams, however many you've overcounted goes in the middle there. So there were 16 people with blue eyes. So I need 16 in the blue eye circle. I've already got 5, so there will be another 11 in the blue eye circle. And in the blonde hair circle, there are 5 who are there already, so I need 3 more for the blonde hair circle. And then the 11 that are neither go outside both circles. And you can see 11 plus 5 plus 3 plus 11 is equal to 30. So let's find the probability someone has blue eyes given that they have blonde hair. So what I'm saying is, I know they have blonde hair. I know that they're in this circle. What's the probability that they have blue eyes? Well, you can see there are 8 people to choose from and 5 of them have blue eyes. So it's simply 5 over 8. So what's the probability they have blonde hair given that they do not have blue eyes? So now what I'm saying is I know they don't have blue eyes. I know they're definitely not in the A circle. So there are 11 plus 3. There are 14 choices for students who are not in the A circle. So of those 14, how many have blonde hair? So out of these guys, how many have blonde hair? The answer is 3. 3 out of those 14 students do not have blonde hair. You can see that these probabilities were calculated so much easier due to Venn diagrams. All right, let's now look at two-way tables. So two-way tables essentially do the same thing as Venn diagrams. They can be useful, however, when we have information about totals, because two-way tables, unlike Venn diagrams, have a row and column for totals. So two-way tables look like this. So just like Venn diagrams, they're helpful for two sets. So we're going to put set A, not set A, set B, not set B. So they will be very useful in answering this question. So surveys conducted of teenagers. 56% were boys. Of the boys, 75% have never smoked before. It was also found 72% of all the people had never smoked before. So we're going to select a member of study at random and calculate the probability they are a boy given that they have smoked tobacco before. So all of this information is very confusing. It would be hard to calculate this probability without some way to organize all of the information we're given. So that's what the two-way table will do. So there are two sets here. Firstly, we're talking about whether they're a boy or a girl. The second bit of information is whether or not they've smoked before. So I'm just going to let S stand for that they've smoked before, and this, of course, means not S. They've never smoked before. So now let's put in the numbers. So 56% of students were boys. So that goes in the total here. We wouldn't be able to put that 56% in a Venn diagram. So, of course, if 56% were boys, then 44% were girls, because 100% would be the total. We're also told 70% of students have never smoked before. So 72% goes there. Obviously, that means 28% goes here that have smoked. So we don't have enough information to fill in these 4 unless we have this information that 75% of boys have never smoked tobacco. That's actually a conditional statement. The probability that someone has never smoked, given they're a boy, is 75%. So we're talking about boys who've never smoked. We can't put 75% here because these two cells only add to 56. What we do instead is we're finding 75% of those 56% boys haven't smoked. So on your calculator, you just put 0.75 times 56, you get 42. 42% is the number that goes here. 42% of all people in the survey are boys who've never smoked. So having that number, we can find the rest of them. So obviously 30% would go here because they add to 72, and then 14% would go here, and 14% would go here. So now we've displayed all of this information in a visual way. Now let's find the probability that someone is a boy given they have smoked before. Well, this is going to be a lot easier now. They have smoked before means they're in this row here. So that's 28% of all people. So the probability that they're a boy is just 14 over 28, which is 50%. So that's basically saying of the people who have smoked, half of them are boys and half of them are girls. Okay, so that's all for probability. Now let's look at the functions work. So we'll start with graphing functions. So I'm going to go through graphing lines and parabolas. So to graph a line, you only need to find 2 points and join them. You can use the xy-intercept or the gradient-intercept method. So let's firstly graph the line y equals 2x plus 3. So that's an easy one to graph. This is the y-intercept. So all we do is mark the y-intercept. The first number is the gradient. So it's 2 or 2 over 1. So that means for a line, we go across 1 and up 2. That's what a gradient of 2 means. And then we just join up these lines like so. So the gradient is the number in front of x only when it's in the form y equals mx plus b. If it's not in that form, you can't read the gradient and intercept off just like I did. You might need to use the xy-intercept method. And that would be just letting x equals 0 to find the y-intercept and y equals 0 to find the x-intercept. Alright, so for parabolas, we find 4 features and then just plot them and join them up. So I graphed the line. Let's now graph the parabola y equals x squared plus 6x plus 8. We'll find these 4 features. So remember that we write the general form of a parabola as ax squared plus bx plus c. In this case, a is 1, so it's monic, b is 6, c is 8. So A determines the orientation. If A is positive, it's a smiley face, and negative, it's a frowny face. So because the number in front of x squared is 1, this will be a smiley face. Next, we find the y-intercept by letting x equal 0. So if x equals 0, y would just be 8. So the intercept here, the y-intercept, is 8. So to find the x-intercepts, what we need to do is let y equal 0. So we've got 0 equals x squared plus 6x plus 8. You can use the quadratic formula for this one if you want. It's probably easiest to factorize. So finding 2 numbers that multiply to 8 and add to 6, we factorize it like so. So null factor law, either the first bracket equals 0, which would mean x equals minus 4, or the second bracket equals 0, x would be minus 2. So that means that the 2 intercepts are minus 2 and minus 4. So to find the turning point, x equals minus b over 2a. So in this case, b is the number in front of x, a is 1, x equals minus 3. That's the x-coordinate of the turning point. But a point needs a y-coordinate. So to find the y-coordinate, we simply substitute that into our original equation. Take minus 3 and put it in here. Whenever you're substituting a negative, always use brackets. Otherwise, you'll make a mistake here. So if we put that on the calculator, we actually get -1. The turning point is -3, -1 there. So because we know it's a smiley face, it's just going to go up like this and hit 8 and just be symmetrical. So that is the graph of the second parabola there. So now let's look at the opposite. Let's look at finding the equation of a function. So how we find the equation of a function depends on what kind of function it is. So firstly, for a line, we just need to find m, b, and then the equation will be y equals mx plus b. For parabolas, we're going to use simultaneous equations, and for hyperbola, we need its graph. Let's start with a line. So let's find the equation of a line that passes through these 2 points. So we're just going to follow the steps above. So the first step we're going to do is to find the gradient. Because we're given 2 points, we use the 2-point formula. M equals y2 minus y1 over x2 minus x1. So we get 12 over -8, which is -1.5. That's the gradient. So that means for this line, each time you go across 1 to the right, you'd go down 1.5 units. So the way you find b is to take your equation, y equals mx plus b. We can do that because any line can be written in this form. So you take your equation, we substitute m, so m in this case is 1.5, and we substitute x and y. So x and y come from one of the points. Either one doesn't matter. So I'm going to choose this first one here. So I'm going to substitute x for 3 and y for -4. So I get -4 equals -4.5 plus b. Add 4.5 to both sides, you get 0.5 equals b. Therefore, the equation of this line is y equals mx plus b. All right, let's look at parabola. For a parabola, you need 3 points, whereas for a line, you only need 2 points. So 3 points for a parabola, and you use simultaneous equations. So let's say I'm given these 3 points, and I want to find the equation of a parabola that goes through them. So the equation of any parabola is of the form y equals ax squared plus bx plus c. I just need to find a, b, and c. So this point here tells me that c equals 3, because this is the y-intercept. C is whatever the y-intercept is. So I know this equation is going to be y equals ax squared plus bx plus 3. Now I'm going to substitute in each of these 2 points and get 2 equations to solve for a and b. So if I substitute in the point 1, 2, so y equals 2, 2 equals a times x squared plus bx plus c. If I substitute in 2, 3, I've now got y equals 3, so y equals a x squared plus bx plus c. So let's just make these 2 equations easier to work with. So this is just 2 equals a plus b plus 3, 3 equals 4a plus 2b plus 3. So now, in each equation, I'm going to subtract 3 from both sides. So move the 3 over that side, move the 3 over that side. So now, I'm going to solve these 2 equations simultaneously. So I'm going to use the elimination method. So remember to use the elimination method. You have 2 variables here, a and b. One of them needs to have the same coefficient in both equations. So you can see neither does here. So I'm going to times this top equation so that the a's have the same coefficient in both equations. So if I times this top equation by 4, I end up getting -4 equals 4a plus 4b. So when I'm multiplying the equation by 4, I multiply everything by 4. I'm going to leave the bottom equation alone. See, now I have that a has the same coefficient in both equations. Now I can eliminate the a's easily. A's are the ones I eliminate because they have the same coefficient. If the coefficients have the same sign, like they're both positive or both negative, the way you eliminate is to subtract the equations if they had a different sign. So, for example, if it was like a positive and a negative, then you would add both equations to eliminate. So, going through here, minus 4 minus 0 is, of course, just minus 4. 4a minus 4a is 0. That's why I'm doing this. I'm eliminating the a's. 4b minus 2b equals 2b. So I get 2b is equal to minus 4. B is equal to minus 2. So now I substitute this to find a. I can substitute this into any of these equations and it would work. This one's going to be the easiest. So if minus 1 equals a minus 2, that means a is positive 1. So the equation would simply be y equals ax squared, 1x squared, plus bx plus c. And that's the equation of the parabola. So to find the equation of the hyperbola, note that any hyperbola, its equation can be written in the form y equals a over x plus h plus k. Now, these values for h and k, they come from the asymptotes. So remember, asymptotes are no-go zones of a graph. So lines and parabolas don't have asymptotes. No polynomial does, but hyperbola do. The asymptotes come about because you can't divide by 0, so x equals minus h is an asymptote because that would make the bottom equal 0. And we also can't have that this fraction equals 0, so y cannot equal k. So these two asymptotes are the red dotted lines. The blue is the graph of the hyperbola. It can never touch or go through those red lines. So h is just the opposite of the value of the vertical asymptote, the x asymptote. So the x asymptote here, the vertical asymptote is x equals 3, so that means h is minus 3. So for the vertical asymptote, h is always the opposite of that value. So for k, it works like you'd expect. The horizontal asymptote is 2, so k is equal to 2. So that's because we now have that the equation is y equals a over x minus 3 plus 2. So that makes sense because this asymptote at x equals 3 means the graph can never go through x equals 3. If I substituted x equals 3, I'd be dividing by 0. That's why h was minus 3. Similarly, we can't have this fraction equal to 0, so that means we can't have y equals 2. And that's why the asymptote's at y equals 2. The last thing we need to do is find a. So to find a, we're going to substitute in a point, a value for x and y into this equation. So we just pick a point that's easy to see. So this one here that's marked is the point 4, 0. So I'm going to substitute into this equation y equals 0 and x equals 4. So I get this. So that, of course, means 0 is just a over 1 plus 2. So subtracting 2 from both sides, a equals minus 2. So therefore, the equation of this hyperbola is y equals a over x plus h plus k. And then we're done. So the final thing we need to look at is polynomials. So a polynomial is a linear combination of non-negative integer powers of x. What that means is it's an expression of the form of something plus something times x plus something times x squared plus something times x cubed plus something times x to the power of 4 and so on. So here the powers of x can only be positive integers. Otherwise it's not a polynomial. So for fx equals 3x, we usually call polynomials f of x. So fx equals 3x, that is a polynomial. The only power of x here is x to the power of 1. Well, that's a positive integer, no problems. This here is a polynomial as well, because the only powers of x, 3, 2, 1, are positive integers, and there's a constant as well. So this third one here, this is a function, but it's a hyperbola. Hyperbolae are actually not polynomials. So the reason this is a function, remember that graph on the previous slide that was a hyperbola? It's a function because, like polynomials, it passes the vertical line test. If you draw a vertical line, it will only hit the graph at most once. So it's a function, but not a polynomial, because x is on the bottom of the fraction. That actually means x has a negative power. So we can't be dividing by x in a polynomial, only timesing by x. And this last one here, that is also not a polynomial, because the square root of x is the same as x to the power of a half. It's not an integer power of x. So these two are polynomials. Now, one thing we need to do is to be able to factorize polynomials. So I'm going to take this one here, we're going to factorize it and solve it. So let's take this as our polynomial fx. We're going to find all solutions to fx equals 0. Now, usually you need to be given a solution to start with. If I substitute f of 3, what that means is I take x and change it to 3. So I'm going to change x to 3 in all of this. So the value of f of 3 is 10 times 3 cubed, 10 times x cubed, minus 9 times x, which is 3, squared, minus 73 times 3 plus 30. So it turns out f of 3 is equal to 0. So that is one solution to this equation. As I said, you'll usually be given the first solution to the equation. So how do we find other solutions? So this is a cubic. It's a degree 3 polynomial. That means it will have up to 3 solutions, and we've only found one of them. So to find the others, we're going to use polynomial long division. Now, the factor and remainder theorems say that if f of 3 is equal to 0, x minus that number, x minus 3, is a factor. So what I'm going to do is I'm going to use polynomial long division, x minus 3 into this polynomial. So this is how we do polynomial long division, dividing one polynomial by another. So we go leading term into leading term. 10x cubed divided by x gives me 10x squared. So whenever I get something up the top, like I do here, I then multiply it by this linear factor. So I go 10x squared times x, 10x squared times minus 3. Now I'm going to calculate the remainder. I do that by subtracting. So 10x cubed minus 10x cubed is 0. Minus 9x squared minus 30x squared gives us positive 21x squared. Whenever we've got a remainder, we divide by the leading term. So 21x squared divided by x is just positive 21x. Now we repeat the process. When we put something up here, we times by the linear factor. So what we're going to do is bring down this minus 73x to compare it. We go 21x times x is 21x squared. And then we go 21x times minus 3 is minus 63x. We calculate the remainder by subtracting. Minus 73x minus 63x just gives us minus 10x. So minus 10x divided by x, we get minus 10. So we're going to bring down the 30, and we're going to times minus 10 by x, gives us minus 10x, and then minus 10 times minus 3 is positive 30. If we calculate the remainder one last time, we get 0. That is the remainder of the whole thing. So x minus 3 times this is equal to that. So the factor theorem says because we got a 0 remainder, x minus 3 is a factor. And that's what we should have got. We already knew x minus 3 was a factor. If we didn't get a remainder of 0, we would have done something wrong. So what I've actually figured out is that this polynomial fx, I can write it as x minus 3 times by this quadratic. Now that makes things a lot easier because we know how to factorize quadratics and they're so much easier to work with. So this is what we're going to do. So we're going to leave the x minus 3 alone, and we're going to factorize this quadratic here. So because it's non-monic polynomial, because the leading coefficient, the coefficient of the greatest power of x, is not 1. It's non-monic, we need to use the AC method. So the AC method, we times a by c, we get minus 100. We now need to find two numbers that multiply to negative 100 and add to 21. So those numbers are actually 25 and minus 4. So we split up the middle term into 25x minus 4x. So then what we do is we factorize the first two and factorize the last two separately. So factorizing the first two, the highest common factor of 10x squared and 25x is 5x. So we get 5x outside of 2x plus 5. And then factorizing the next two, we're going to take out a negative factor this time. The highest common factor of negative 4x and negative 10 is minus 2. And then we're left with 2x plus 5. So when you're factorizing a non-monic quadratic, these two brackets should be the same. So what this actually ends up as, fx is equal to x minus 3. The final step in factorizing this is we take the thing that's in the brackets as our new common factor, write that out the front. So 2x plus 5. And then what's left goes in the other brackets, 5x minus 2. So if fx equals 0, we can now use the null factor law. Either this first bracket equals 0, which means x equals 3. We already knew that. So either x equals 3 or this bracket equals 0, which would mean x is minus 5 over 2. If 2x plus 5 equals 0, subtract 5, divide by 2, you get x equals minus 5 over 2. So the other possibility is 5x minus 2 equals 0. So then you would add 2 to both sides and divide by 5, and you get positive 2 over 5. These are the three solutions. And we know there will be no more solutions because a degree 3 polynomial can never have more than 3 solutions. Alright, sorry again for a long video, but best of luck studying for your exam. You're a superstar. You will ace it. Thanks so much for tuning in. This has been the luckiest maths teacher in the world. Have a great day.